Welcome back in our continued discussion of this wind energy. So now, what we're going to talk about now different technological development that has happened so far, and uh, then what are the challenges that one can face, and some of the component-wise issues. So that's what now the topic that we are going to cover is on wind turbine technology. So it's more like an giving a complete overview of the technological progress that has happened so far. Some of them probably we might have already discussed upon. And then what we would like to take you from there is that um, this technological advancement that has taken place so far, where we stand in terms of technological challenges, then what are the issues that you have as a need of the hour, and then how we can improve our system or design and things like that. This is important in one hand is that just getting to the more like an group of this discussion of this development, and then from there slowly we'll kick off on the aerodynamics part of it. I mean, and then move on to the design constants and things like that. Okay. So what we are going to talk is more on the turbine side and turbine technology. So the thing has to start with is the installations. So what is a situation at this moment? Obviously, these are taken from this global energy report. What is the status at this moment? And then what is the projection that we have? So if you look at the situation at this moment, the new installations are almost globally 76.6 gigawatt in 2022, and then bringing total installed wind capacity of 906 gigawatt, which is a growth rate of 9%, which is compared to 2021. So in between 2021 to 2022, there is a substantial amount of increase in the new installation across worldwide. And the important players there, obviously China, US, Brazil, Germany, Sweden. Altogether, they made up 71% of the global installation last year, collectively 3.75% lower than 2020. Obviously, when you talk about this, the new installation, this has to do with a lot of other economical challenges that every country would face. So, say their market value, new partner, in investments, it has to do with a lot of other economical balances to take care into the system so that it can talk about these things. Now, up to 2022, the spread across different subcontinent is different. Obviously, this graph shows how this, again, this report was there in 2023. That is why the data is there tabulated up to 2022. If you see 2020, there is a huge installation, then there is some dip between that portion. But one of the important thing to be note here, majority of the installations in uh, onshore instead offshore. Now, if you go to North America, you have 60 gigawatt of onshore wind capacity expected to be added in next 5 years, which will be 92% built in US and the rest of the Canada. Europe, with strong demand with Germany, Spain, UK, France, Italy, Turkey. Obviously, UK is out of that European Union though. 2024, then Africa has 17 gigawatt of new capacity expected in 2023 to in the span of 5 years up to 2027, out of which 5.3 gigawatt would come from South Africa, 3.6 from the Egypt, 2.4 gigawatt from Saudi Arabia, 2.2 from Morocco. If you go to Latin America or Southern America, obviously 26.5 gigawatt of onshore wind to be added in this region in next 5 years over Brazil, Chile, Colombia contributing total 78% of the additions. Okay. We have this kind of new installations which are going to come over for next 4 to 5 years. Now, what is the projection? The projection for 2030 is quite heavy, or I would say the obviously every country is taking different measures, different national-wise policies. Somebody would like to reach some target by 2030. Some countries would like to reach target by 2035, some by 2040, 2050. These are global, worldwide, some scenario, and this is what by 2030. So global wind market. So what it there is that capacity buildup of 143 gigawatt. So obviously, key reasons behind this upgrade include energy system reform in Europe. They try to replenish the fossil fuels with renewables to achieve energy security in aftermath of Russia's invasion of Ukraine. China's commitment to further expand the role of renewables in its energy mix and anticipated 10-year installation uplift the US driven by IRA and all. So you see this curve, what is projected is quite heavy. What is the total cumulative global installation that is expected? So it's a 2 terawatt milestone is expected to be achieved in next 6 to 7 years. So that's quite a bit of humongous target. But yes, every country who are having the feasibility to exercise this wind energy harvesting capability, they are into the game and they try to do this process. And there are some onshore demand, there are some offshore demand. So obviously, onshore wind demand and some benchmark, China demands or dominates the global onshore wind turbine, which is within 82 gigawatt of identified annual capacity. Europe is the world's second largest onshore turbine production base, followed by US 13.6 gigawatt. India is also not very bad, which is 11.5 gigawatt, and then Latin America. So the supply chain in India, China, Latin America will have enough national production capacity to accommodate demand, while the rest of the world in a business as usual scenario will continue to rely on imported wind turbines to cope up with the anticipated growth. So this is onshore installations talking about that. Now, when you go back to the offshore demand, within a projection between 2023 to 2030 or 2030 or 2031, compared with onshore demand, the chain of offshore wind turbines is more concentrated due to the fact that the more than 99% of total offshore wind installation is presently located in Europe and APAC region. Yes, I mean, having said that, China is world's number one offshore turbine nacelle production center with annual assembly capacity of 16 gigawatt, of which 1 gigawatt is owned by own Western turbine manufacturer. So these are the situation challenges in terms of demand production chain. That means what we would like to achieve by 2030 with this kind of production capability, that's quite challenging. So this is a wind farm and Pincer Creek in Alberta, which just to give you an idea, this is a picture that how the farm is installed and all these things. But you have to keep one thing in mind, that whenever this farm installation is taken care of or done, so there are plenty other things need to be taken care of, because one is planning to install this kind of farm, I mean wind farms, and sure it is optimized in terms of every aspect. Okay, but there are challenges. I would say there are challenges for wind farm optimization. So the challenges, in a sense, this is slightly away from your single turbine optimization. So one hand, you can talk about single turbine optimization, but when you talk about the wind farm optimization, these are the different challenges that you have. Here, you have to optimize collectively group of or set of turbines positioned together. Again, expected growth or offshore turbine size globally, which we have already talked about that. Again, I would like to re-emphasize, because we are somewhere here close to 8 megawatt, projected by 2030, 11 megawatt, and the one design that we are talking about in a real, now working on a 15 megawatt turbine. So people have been doing a lot of research on that. So that's the projected path. So in this path, key challenge is that the design, manufacturing. Okay. So design includes everything. So we'll talk about those things later on as well. That is like talking about the aerodynamic design, talking about the structural design, how they are coupled or interlinked. So these are the things that we would be discussing in details as we move on with our discussion. Offshore turbine, the turbines for offshore application is also growing from 4.1 megawatt in 2015 to 11 megawatt by 2030. But there have been discussion of offshore turbine reaching 15 megawatt and even 50 megawatt capacity. So this is a key challenging area, because more and more power that you would like to generate, the thing that is going to be, because power is higher power is proportional to higher area. So that means higher D, rotor diameter. So more and more larger rotor diameter, so that's going to cover a larger swept area. So once you have larger swept area in that fashion, you need serious development in terms of materials as well, because the larger turbine is going to be, even a three-bladed turbine is going to have a huge weight to carry. And the important part is that these blades are going to be in rotating frame of reference. That means there is a rotor which has to hold this and then rotates for generation of power. Then you have yaw mechanism, pitch mechanism. These drives are also sitting inside the nacelle, and they have to kind of move these turbines blades depending on the wind direction to accommodate the wind availability. So the challenge here is that also the, apart from your aerodynamic design, apart from your structural design, you need light material or literally ultra light material, so that there is no extra load that comes on the tower or the foundation and things like that, and also the rotor mechanism, because these are mechanism. If you have a, because if you have a too larger area and this is a rotating body, there is a chance of damage or collapse due to this dynamics of the system. So we'll be talking about the dynamics, vibrations partly, and quickly try to see about that. So key thing is that as you grow or expect to have more power producing capacity with larger diameter, you also need to have ultralight component materials using C fibers, composites, and things like that, so that you can have less weight on the structural design column. Okay, you can see some example of power cards for wind turbines with different rotor diameter. This is 80 meter, 87 meter, 90 meter, and the power generating capacity 2 meter. So this is a wind speed which is exposed to, and these are different diameters. I mean 80, 87, 90, and all are rated or capacity is 2 meter generator. So you can see what happens is that even the 90 meter diameter turbine, once you increase the wind speed beyond 20, 21 meter, it drops. Other two remains flat at that rated power. Now, one can immediately think about why this is happening. This is happening because once you have larger rotor diameter, once you increase your wind speed, your turbulence levels are also going to increase. So once that happens, there is a likelihood chance of separation is taking place, which we are going to talk about soon. That separation is going to taking place over the blades or rotating blades. So those separations are going to cause increased drag, and that's why subsequently you will have drop in the power production. Okay, so because these are different kind of challenges one face in rotating machines. I mean, I would consider this wind turbine is like a rotating machine. If some of you are mechanical engineers or electrical engineers, you know how these rotating machines work. I mean, for mechanical engineer, you have seen pump, turbines, I mean, steam turbines, gas turbines, compressor. These are rotating machines, fans. So the rotating systems are a bit challenging to handle. So there are always would be a range where you can operate very nicely or with an optimal way. As soon as you go beyond certain level, there could be a drop in your output. So what is causing that thing? So as we have talked about it, when the wind passes over those airfoil or the rotating blades, which are, I mean, if we just draw a blade like that, which is connected to the hub, and if this, so at different locations you have, these are the aerofoil shape that you have over which the flow passes. And once the flow passes over an aerofoil, typically due to this theory of aerofoil, there is a two forces which are going to be coming out of this. One is the lift force, another is the drag force. Now, for aircraft, the lift force is required to take off. Drag is required when it touches down or during landing. Here, the lift is what makes the rotor to rotate. So that once it rotates, that's why the rotating motion gets converted to that electricity production. So the aerodynamics of a wind turbine have much in common with the aerodynamics of a aircraft wing, but obviously with some differences. So this should be slightly much bit clear. So you can see this is my rotor, and this is hub, and this is the tip, and this is how it is rotating. So this is an section where you can see, obviously this is the wind direction, and is kind of an aerofoil section which has been projected here. Then this aerofoil is exposed to different component of these velocity triangles. And finally, what you get out of is the lift force, drag force, and their components. But the aerofoil is exposed to different angles, flow angles, angle of attack, pitch angle, and all these things. So these are the details of these things that will work out later on. But similar kind of things happens on the airfoil wing. Same thing you. So that's the similarity. But so here the only difference between the aircraft wing or this is that these forces are going to, especially the lift force is going to rotate the turbine so that you have generation of power. So this angle distribution of the forces that again we will see in details, and then from there we try to see how we get these productions of the power. So now once you talk about power productions or energy productions, the key player is the efficiency. We have seen earlier that we talked about some limit like bridge limit, we talked about some transmission efficiency, we talked about some of this mechanical gear efficiency and some of these things. So when you talk about the wind turbine efficiency, it's a simple thing to characterize. It's that the amount of electric power that is produced to the wind passing through the area by the rotor blades or the wind power. So it's the wind power, how much wind power converts to the electrical power or electrical generation. Because when the wind passes over this, when the wind passes over this aerofoil or the passes over these rotating blades, so they allows these blades to rotate, and that motion getting converted to this production of the electricity. So the amount of electricity or electric power produced and how much is wind power getting in, that's what the efficiency of a turbine. Obviously, one of the important efficiency factor is the aerodynamic efficiency, which is the nothing but the ratio of the mechanical power of the rotor to wind power. That means how much wind power I give an input and how much I get an output as a mechanical power. So that's how the aerodynamic efficiency, because the wind power is purely aerodynamic power, and that's the conversion efficiency, how much I will get into the mechanical. Now then I have mechanical efficiency, which is again connected with the mechanical rotor axis generator and all these things. So there would be these machine components which has this conversion efficiency that it doesn't convert the completely amount of this thing. Then you have electrical efficiency. So that is the electrical power fed into the grid to the mechanical power of the generator axis. That means I have stage-wise these efficiencies. One is that the wind, which is when the air passes around these turbine blades, how much wind power one can generate from the aerodynamic point of view, and that wind power, how much is getting. So that's your aerodynamic efficiency. And that using that, how much can be the generator axis gets a power which is mechanical efficiency. Then the generator power to how much electric power would be output as the electrical efficiency. So all these efficiencies are going to affect. So that means wind power, which is from the aerodynamics point of view, multiplied with this efficiency, that much converted to the electrical output. So that's a total efficiency of my wind turbine. That's how you characterize this thing. So the maximum possible aerodynamic efficiency is given by the Bayes law or Bayes limit, which is 59.3%. So which occurs in turbine by 2/3 of its original speed. Aerodynamic efficiency of a real turbine varies with wind speed, having a typical peak value of 44% and average values of 25%. So what happens is that typically the mechanical efficiency is order of 96 to 99%. Electrical efficiency is order of 96 to 97%. Then multiply these efficiencies, get the overall efficiency. Obviously, if the overall efficiency, then mechanical efficiency, electrical efficiency into base limit or redundance efficiency. So all this efficiency multiplied together gives the overall efficiency of the system. That's how you get these efficiencies into place. Now, if you look at the output versus efficiency, okay, so you can see the variation of the power output efficiency with the wind speed. So this is again a typical series. This is N90 is the 90-meter rotor diameter, 2.3 megawatt is the output. X-axis shows the wind speed, and this side is the efficiency. This is the output. So you can see how efficiency is getting into that constant line with change in wind speed. So beyond the wind speed, there is no change in the efficiency. That becomes pretty much after this point, one can think about that means beyond 13 meter per second, this efficiency. Obviously, this car is particular. So one has to have different turbine map for that. And then this is the output. So up to a certain the maximum output, and then you get to see this is the max output you have, and then there is a down once you increase the wind speed. So that means your power output, again, this kind of curve can be generated for different kind of turbines, because once you change the diameter of the turbine, then that's going to change the characteristics of this curve. But what this is an example, or for I mean taken for this particular turbine. This is just to showcase how this output varies with the wind speed, how the efficiency varies with the wind speed. So what is clear here is that if you keep on increasing the wind speed, or if your turbine is exposed to very high wind speed, neither your output power is going to be more, it rather decreases. And that means there is always an optimum range of wind speed where a particular turbine can produce the maximum power, and there is a range where your efficiency goes to maximum, and after that it remains constant. So that's the key message here, that every turbine has an operational limit, and that is coming from your design parameter. So if your turbine is exposed, or if you try to operate your turbine beyond that limit, then you are going to have an reduction in your output in terms of power output, in terms of efficiency, everything. So that's how one has to think about it in designing the system. Okay, so we'll stop the discussion here and continue about this different aspect of the technological part of the wind turbine in the subsequent section. Thank you.